quick video explaining a very basic thing. It's a derivation of a magnetic field at a certain point by using Biot-Savart's law. It's a derivation, so there's a high chance it's going to come in exam. And it's a very simple one. One is of a circular current carrying loop, and at the center of the circular current carrying loop, another is on the axis passing through the center of the circular current carrying loop. Very simple. First we'll do at the center of the current carrying loop. So this is a circle with a center point P, radius capital R. This is a current carrying element dl, very small, infinitesimal, I'm not sure how to pronounce that, infinitely small current carrying element. As you can see, this is like a tangent to the circle. So a tangent is always perpendicular to the radius of a circle. So that's why we'll use this later in the derivation. You will see. So according to Biot-Savart's law, dB is equal to mu naught by 4 pi current into dl cross r by r cube. This is the unit vector of r basically. Now when you take dl cross r, you get dl r sin theta, right? So this r and this r square will cancel and you'll be left with r square here, and you'll be left with dl sin theta. dl sin theta. So now is where we use that 90 degrees over here. So that this is the sin theta is the angle between this dl and this radius. And the angle between that is 90 degrees because it's a tangent. So this will be sin 90, which will be 1. Again, we can remove that. Now, all we need to do is we need to integrate it on both the sides. So all this is constant, it will come out. Now the integration of dl is all these small elements that are going like this, like this, like this. It's all going around the circumference of the circular current carrying loop. So that means that when you add all these parts, you get the total circumference of this current carrying loop. So integration dl will be 2 pi r, 2 pi capital R. This is also r square, my bad. So you get 2 pi r. And when you substitute it back, so over here you get b is equal to mu naught I 4 pi r square into 2 pi r. R cancel, pi cancel. It will come like this. B is equal to mu naught I by 2r. This is the magnetic field for the circular current carrying loop at the center of the loop. Now we will see at the axis of the circular carrying loop. Again, we take the same two elements, dl, radius is again capital R. Now, what we mean by the axis passing through the center of the loop is that it's not at the center, but it's at some point away from the center. So say it's over here, and this is valid for any point on the axis. So I can take it here, I can take it here, I can take it here. So like for example, if I take it here, P, dl to P will be R, which is our displacement that comes in the Biot-Savart's law. Over here also like this, R. Now I've taken these two because this means that this is representing the magnetic field at this point due to these two current carrying elements. We can write dB, and say this is the normal. This is theta. This is also theta. Actually, we don't, or yeah, maybe we do. I'll just write it down later. So what's happening over here is, and this is as well, from the center, the distance is x. So now we can calculate a number of things from here. First of all, we can see that when we resolve this into its components, dB sine theta comes like this, and dB sine theta comes like this. Now this is very interesting because now we see that this is valid for all the diametrically opposite endpoints. So it has to be diametrically opposite, and it will come like this. So that means both of these have the same magnitude, but they are in the opposite direction, so they will cancel themselves out. So that means there is no sine theta component there in our actual magnetic field. There's only cos theta component, because what is happening is the cos theta, both are getting resolved in the same direction with the same magnitude, so they are both adding up. Over here, they're getting cancelled out. So there's no sine theta component at all in our final magnetic field. And because it's happening in an entire circle, all there's for every point there's going to be a diametrically opposite endpoint. So all of it will cancel itself out. So we don't need to take this anymore into any consideration whatsoever. And now we can see that this is theta, this is 90 minus theta. This is, since we're taking cross product of dl into r, and that will give us the direction of the magnetic field, we can see that again over here and we know that from cross product, the final result will always be perpendicular to the other two vectors. Like we can see from the right hand rule, this, say there's two vectors like this to this cross product is always coming out. It's always going to be perpendicular to both of these vectors. So dl and r is going to be perpendicular to this. So that means that this angle, the angle with r and dB, is going to be 90 degrees. This is 90 minus theta. This entire angle is 90. So this will again come out as theta. Now if this comes out as theta, this is 90 minus theta, and then this comes out as theta. Now if that comes out as theta, we can find the cos theta. Cos theta will be r by r. Now this r, since it's a right angle triangle, we can use Pythagoras theorem. You get r square, this is the hypotenuse, plus is equal to x square plus r square, right? So we can substitute that here, root over x square plus r square, this comes. Now again from Biot-Savart's law, we know that dB is equal to mu naught by 4 pi I dl sine theta by r square. Now again we know, small r square. Now again we know that because it's perpendicular to this, then that's why this sine theta will again come as sine 90 and it again get removed. And now this r square we can write as r square plus x square. Since it's this, we know that from here r square is equal to x square plus r square. Now we can now we know that since there is no sine theta component, so we know that our final magnetic field is only the integration of dB cos theta. We know our dB is this, and we know the cos theta is this. When we multiply both, we can find our final magnetic field after integrating them, their product. So when you multiply cos theta with this, you get dB cos theta, or we'll say B is equal to integration of mu naught I by 4 pi, and since we're multiplying this with this is summation of the powers, so r square plus x square 3 by 2, and of course we have our dl over here multiplied with another r. Now we see that when we integrate this, of course all of these are all mu naught I 4 pi and r square plus x square to the power 3 by 2 and r, they are all constants. The only variable over here is dl, and we've known from before that integration of dl will just give us back the circumference because of all these, we're adding all these elements. So we get b is equal to mu naught I dl r square into 2 pi by 4 pi r square plus x square 3 by 2. I got this. From there we get that b with pi cancels, 2 like that will cancel. We get mu naught I r square by 2 times r square plus x square to the power 3 by 2. Now from here we get another important relation. This is x square, right? This is the distance from the center. Now what if we take it at the center itself? This x will be 0. If this x is 0, so you get r square to the power 3 by 2. R square into square root, so it will just be left with r, and r cube. So you get r cube over here. There's r square in the numerator. R square cancels this denominator, and you're left with mu naught I by 2r. This is exactly the result that we got in proving the circular loop. So this is valid for everything. That's it. This is for Biot-Savart's law, that's there only in NCERT. Ampere's circuital law is to prove all the other shapes. That's all there is.